Okay, in this video I'm going to try to explain Lenz's law to you. Now we know how to calculate the induced EMF in a coil of wire. We know the induced EMF is the rate of change of the magnetic flux. But what we don't know is what direction will the current flow, and that's what Lenz's law tells us. A current produced by an induced EMF moves in a direction so that the magnetic field created by that induced EMF, or by that induced current, so that a magnetic field created by that induced current opposes the original change in flux. Okay. That's Lenz's law. A current produced by an induced EMF moves in a direction so that the magnetic field created by that induced current opposes the original change in flux. Suppose that you have a situation where the magnetic field points north and it's increasing. Well, if it points north and it's increasing, then the induced magnetic field is going to point south to oppose that change. But if the original magnetic field points north and it's decreasing, the induced magnetic field will actually point north. It will oppose the change. Okay? So basically, the induced magnetic field, I'm going to call that B induced, tries to maintain the status quo. If the magnetic field is decreasing, it's going to try to increase. It's going to add to it. But if the magnetic field is increasing, it's going to go in the opposite direction and try to decrease it. All right, we'll draw some pictures of that. That'll probably be helpful. We also probably need to review a right-hand rule. And that is, we need to remember what the direction of magnetic field is for a loop. If I have a loop of wire like this, and my current goes that way, I can take my right hand and I can put it with that current, and I see that this is going to cause a magnetic field out of the board, the way I've drawn it. If I have a similar loop, but this time the current is going this way, well, now if I take my right hand and I try to curl with the current, I realize my thumb goes into the board. So I know that B points into the board. So you need to know that rule. That's going to help us when we try to apply Lenz's law. That right hand directions with the current, that produces one out. If I go this way, currents this way, that produces one N. Okay, that's just our quick review of that right-hand rule. So let's look at a couple of examples. Suppose that we have a magnetic field, and it points up and is increasing. Let's see if we can find the direction of the induced current. So here's my picture. Here's our current loop. And it's got a magnetic field that points this way. That's the original magnetic field. But it's growing. It's getting bigger. It points up and it's increasing. If it points up and it's increasing, then the magnetic field that's induced is going to point down. It's not pointing down because the original magnetic field points up. It's pointing down because the original magnetic field is increasing in the upward direction. So it's going to point down. Okay. If I looked at this same picture from above, let's picture this from above. Well, if I picture it from above, if I want the magnetic field to point down, I don't want it, the original field is coming out of the circle. I want the induced one in. I want the induced one in. Then I need the current to go this way. So the induced current is clockwise. A lot of times we just abbreviate that CW when viewed from above. Now, that's one of the tricky things. How you're looking at it makes a difference. If you happen to be down underneath the loop and you were looking at it from the other way, it would appear to be counterclockwise to you. But from above, the way I've drawn it, our induced magnetic field needs to go down. So the original's coming out, our new one goes down. That means that current is going to be clockwise when viewed from above. So that's our first example. Let's keep the same thing in though, if we have the same magnetic field, and it's up, but it's decreasing. So here it is. It points up, but it's not getting bigger. In fact, the change is going this way. It's getting smaller. Well, if it's getting smaller, that means my induced EMF is going to try to shore it back up. It doesn't want it to decrease. The induced really wants everything to stay the same. So my induced is now going to be upward. Okay. If I draw the picture from above, if the induced one is upward, it now looks like this. It's coming up out of the top. To do that, that tells me that my induced current is counterclockwise. So CCW when viewed from above. I'm not going to write the words when viewed from above. Exactly the opposite. Okay. We can do this in lots of different directions. I'm going to erase all of this. Look at a couple more examples. a loop that's this way, and we have these to the right. But it's decreasing. So here's my original magnetic field, but it's getting smaller. There's less flux going. That means my induced one's going to also be to the right. It's going to try to short up. So I just need to think about it. If I take this right hand, if I want it to be right, it's got to curl this way. If I look at that, kind of rotate that picture out, if I'm looking at it from the right, I want that induced field to be out, coming directly at me, which means I want it to be the induced current is counterclockwise when viewed from the right. Lenz's law. The induced current is always such that the magnetic field that it makes opposes the change in the original magnetic field. So let's do another example. This one also is one out of your textbook, so you can go back and you can read it in your book and maybe fill in if there's any detail or more explanation that I omit. This is example 29-5. Pulling a coil or a loop from a magnetic field. Okay, so we start with a situation where we have a magnetic field. And it's going to point into the board. I like into the board because it's, to me, more obvious when you draw it. It's easy. Okay, in that magnetic field, right up next to the edge, this is kind of a boundary here. On this side, the magnetic field is 0.6 Tesla. Over here, the magnetic field is 0. Okay? And we're going to have a loop that's sitting in this magnetic field. Here it is, right up against the border. Initially, you can see that the flux, the area of the magnetic field is the entire area of this square. And this is a 5 centimeter square on each side. So we've got 5 centimeters on each side of the square. Okay. We're going to actually take this and we're going to exert a force and we're going to pull it so that it ends up over here. When we do that, the amount of flux through that loop is going to change dramatically. So let's find the amount of flux at the very beginning. And we've got to write down a whole bunch of details about this particular loop. It's not a single loop. It's a 100 loop square coil. So I drew it square, but I did mention that it's actually 100 turns, and that's why I drew it so thick. It's not a one little piece of wire. Magnetic field, 0.6 Tesla. The resistance of this loop, of this coil, is 100 ohms. We're going to need that later. Okay. The loop is pulled out of the magnetic field at a constant speed in a time of 0.1 seconds. So I started the clock at 0 and I pulled it in 0.1 seconds, all of the loop was out. Okay. The first thing they want me to find is the rate of change in flux. Well, let's think about it. The flux of t equals 0, the initial flux. The flux at 0 is the area times the magnetic field, 0.600 times 0.05 squared. So we start with a magnetic flux of 0.0015 Webers. The flux at 0.1 seconds was 0. I want to find the average change in flux, and I'm going to do it right here. That change in flux is going to be the final minus the beginning. And I'm going to do it per unit time. This is my induced EMF. Change in flux, that's a negative sign over change in flux. So my final is 0 minus 0.0015. And the change in time was 0.1. So that comes out to be negative 0.015 Webers per second. Okay, that's for a single loop. So maybe I better just take that off. That is the change in flux. Okay. If I do it for 100 loops, I can get the EMF. The induced EMF is, that's just change in flux. There's no negative. This final minus initial divided by the change in time. The induced EMF is negative n times delta the change in flux. So that's going to be a negative 100 times a negative 0.015 Webers per second. Units here are going to actually be in volts. If I multiply that by 100, I get 1.50 volts. I think I'm supposed to have 3 significant digits. So for a single loop, we got that much change in flux. But if I use my formula, the negative change in flux times n, and I had 100 loops, I find out that I have a voltage or an induced EMF in that coil that's 1.50 volts. Okay. How much flux did I have to begin with? B times A. How much did I have to end with? Change in flux over the time. Okay. The next question they want to know is how much current. Well, current is going to equal that EMF divided by the resistance. So 1.50 volts, 100 ohms. And that comes out to be 0.0150 amps, or I'll move that 3 places, that's 15 milliamps. Well, I want 3 digits, so 15.0 milliamps. The next question wanted to know how much energy was dissipated while this happened. Well, energy dissipated is power times time. So the energy is power times time. So we have V, that's our induced EMF, 1.5 volts. I, 0.0150 amps, T 0.100 seconds, and I find out the actual amount of energy that was dissipated is 2.25 times 10 to the negative 3 joules. If they had just asked for the power, I would have done the 1.5 volts times the current. Power is VI, but they wanted the energy, so I multiplied it by the time to get joules. Remember, power is joules per second. Finally, they want to know, how much force did I have to exert here to do this? Well, one way we can think about figuring out the force is if we think about work and energy. If I dissipated, if it took this much energy, if it used that much energy, I know that work is equal to force times distance. So the force should equal to the amount of work done divided by the distance. Well, the energy dissipated or the energy used would be equal to the amount of work that was done. So we did 2.25 times 10 to the negative 3 joules of work. The distance we actually had to move everything was simply 5 centimeters. This point had to move over 5 centimeters. Every point had to move over 5 centimeters. So 5 centimeters are 0.05 meters. And the force required came out to be 0.045 newtons. All right, that finishes up that really long section 29.2 about flux, Faraday's law, and Lenz's law. There's one more section that I want to add into this video. It's really short, and then there'll be one more video over transformers. This is about section 29-3. And I want to suggest that you read this section. The math is not hard to understand here, but it's about EMF in a moving conductor. That's often also called motional EMF. It's kind of related to the problem that we just stated, but a little bit different. Let's think about if we have that magnetic field B, and we'll let it point directly into the board again. There's really two ways to develop this formula. I'm going to do the one that I think is the easiest, but you might like the other one, and if that's the case, by all means, look at the book and see what you like. But if I have a metal rod or some other metal conductor, but a rod's an easy piece of wire, metal rod, something like that, and I have it in a magnetic field, and notice the rod is in this, we're going to move it where the velocity is perpendicular to the magnetic field. Now, we know that a metal conductor is full of charged particles, and in particular, it has a lot of electrons that are free to move. It's a conductor, so it has all these free valence electrons. So let's think about the force on a negatively charged particle. If we use our right-hand rule, our right-hand rule says that our fingers go with the velocity or current. They curl into the direction of the magnetic field, so into the board. That gives me an upward force on positive charges. So positive charges would feel an upward force. That means, draw this a little wider, that negative charges would feel a downward force. So free electrons would be compelled to move down this way. Well, the end result is if negative charges move this way, positive charges end up here because conservation of charge. You can pretend the positive charges move, they don't really. But the result is the same. If the negative charges all move to the bottom, this leaves this end with a net positive charge. It essentially has a potential difference between here and here, just like a battery. So simply by pulling this rod through like this, we can induce an EMF. So let's think about how big that EMF would be. We know that the force on any given charge is QV cross V, but since V and B are perpendicular, in this situation that force is just going to be QVB. We know that the work done is force times distance. So the work done on each one of those charges is going to be QVBL. And the L is the actual length from here to here. So to move a charge all the way from the top to here down to the bottom of here, we have to do that much work on it. Our definition of voltage, or EMF, is work per unit charge. So if we do QVBL divided by Q, that cancels out. And we get this. The motional EMF, and it's usually written in this order in your book, is BLD. It makes sense. The larger the magnetic field is, the larger we would expect that induced voltage to be. The longer that piece of metal is, the larger we would expect that potential difference or that induced EMF to be. And finally, the faster we pull it. If we barely move it, we're not going to have much of a force on those charges. We're not going to induce a very large EMF. Okay? There's one problem on your homework, I think, that uses this formula. It's really easy. I do not think you'll have any trouble at all with it. That concludes sections 29.2 and section 29.3. The only other part of this chapter we're going to spend time on is transformers, and that's going to be in the next video.